So far we have been looking at various reinforcement learning algorithms, like we have looked at TD learning, Q learning, SARSA, TD lambda, Monte Carlo, and so on and so forth. Right? We also looked at on policy, off policy, all of this. Right? So there is one particular peculiarity that happens when we are using Q learning. So in all of these algorithms, one of the things that you will notice is that we are making an estimate, right. So we are always making an estimate of what the Q function is. When we are making an estimate of the Q function, we are going to look at the Q value of the state that is going to come after this, right. We are going to look at the Q value of the state that is going to come after this, and depending on what algorithm we are using, we are going to use the actual action that we took, right, the Q value of the actual action we took, or the max Q value in the next state. But then if you think of algorithms like SARSA, the actual action you take will also be the max action more often than not, right, it will be the max action more often than not. So in such a case, it is almost always the the case that the target value that you use for your Q function will always use, or with a high probability use, the current max estimate among all the actions, right. So if you make a mistake in estimating the max, then that mistake will keep propagating, right. So that is basically the idea behind maximization bias. So we will make it a little clearer with an example now, right. So consider this very simple example here. So you have a like a two state really MDP A and B, right. So the A is the starting state always, right, and you have two actions from A. You can either go left or you can go right. Okay, there are two actions from A, left or right, and if you go right, you get a reward of 0 and you terminate deterministically, right. If you go right, you get a reward of 0 and you terminate. If you go left, you get a reward of 0 again, and with probability 1 you will end up in state B, right. From A, if you go left, you will end up in state B with probability 1 with a reward of 0. If you go right, you will terminate with reward of 0 again with probability 1. Okay. Now from B you have the challenge here. From B you have a lot of different actions. Let us say you have some capital N actions, right, this let us say 10,000 actions, right, just to make it extreme, right. So from B you have 10,000 possible actions you can take, all of them with probability 1, right. So all the 10 actions with probability 1 will go to a terminal state, right, and each of them gets a reward. Now this reward is stochastic, okay. This reward is sampled from a normal distribution, right, with mean minus 0.1 and variance of 1. If you remember the original bandit examples that we had, the arms, if you had read the book, right, the arms had a mean of mean drawn from a Gaussian of 0 mean and variance 1, right. But now what we are saying is we are fixing the mean. So you can think of the B as having 10,000 actions, and for each action you are getting a reward from a distribution which has a mean of minus 0.1 and variance of 1. Okay. So what happens? So this means this is going to look like right. So this is minus 0.1, right. So minus 0.1 has the maximum probability, and then it has some variance around it, right. So that means sometimes the reward that you sample will be positive, right, will be greater than 0, right, and most of the times the reward that you sample will be lesser than 0, correct, right. There is some good probability mass that the reward that you sample will be greater than 0. So when you do action 1, okay, from state B, there is a good chance that you get a reward greater than 0, right, maybe not. But if you do 10,000 different actions from starting from B, right, each action you try, then there is some chance that one of those actions will get a reward that is greater than 1, right. In fact, there is a good chance that about 30% of the arms will get a reward that is greater than 1, okay, just remember that, right. So this is something that you keep in mind, right. So when I move from B, about 30% of the times the arm that I take, the action that I take, okay, is going to get a reward that is greater than 0, and other times it will be less than 0, right. So, which direction should you move from A, right? Look, thinking of how you will estimate the values, right? So, the value for going right will be, right. So, what will be Q of A comma right? So, if S naught is A and A naught is right, the return will always be 0, right. There is no question about it, correct. The return will always be 0 if I go right. What about going left, right? What will be the return if I go left, assuming my gamma is just 1, because it is just a one step thing, right. So, it will always, it is an episodic task. So, let us keep my gamma to be 1 just to make things simple, right. If I go left, what will happen? I will go left, I will get a reward of 0, right. So, if I go left, I will get a reward of 0 plus whatever action I choose from B and go and terminate, the expected reward is minus 0.1, right. The expected reward is minus 0.1. So, the total return for going left is 0 minus 0.1, which will be minus 0.1, right. So, the expected reward for going left from state A is minus 0.1, the expected reward of going right from state A is 0. So, what is the action I should pick in state A? Going right, correct. So, right should be the action that I will pick from state A, right. There is no question about this. Now, let us see what happens when we use Q learning. Right. So, when I use the actual return, right, actual expectation of the return going right from state A was the correct action. So, when I use Q learning, what is going to happen is that I will be using this as my target, right, R plus max over A of Q ST plus 1 comma A as my target. So, in this case I will be using Q of B comma some action, right. I am going to look at the Q of B comma some action. Now, think about this, right. We said that there are some actions which are going to have a positive reward when I sample from B, right. So, of these 10,000 different actions, some will have a positive reward. So, what is going to happen is that when I take the max over all actions, I am going to get something that is positive, right. Does not matter if 9,000 of my actions have the correct minus 0.1 as their value estimate. If there are a few actions that have a positive value estimate, the max is going to return the positive value to me, and I am going to use that for updating the value of going left in state A, right. So, this is what I am trying to do here is Q of S comma left, right. So, that is the action that I am trying to update. So, I will use the old Q of S comma left, right, plus alpha times this quantity. So, R which will be 0 plus no gamma. So, whatever is the max over A of Q B A minus Q S A comma left, sorry. Yes, here is A, right, capital A, right. So, this is basically the update equation that I will have, right. So, the problem here is that I am using the maximum over all the estimates I have taken so far. So, the estimates could be erroneous, but I am taking the maximum of that, right, to as an estimate for this maximum of what could happen next, right. A little tricky here, right. So, this always leads to overestimating what the target will be, because I am taking the max over already a set of estimates. Therefore, I will pick a large value, right. Whenever there is an error and the error is high, right, then I will pick the higher value than picking something that is closer to the true maximum. In this case, the maximum should have been minus 0.1, because all actions have an expected reward of minus 0.1, but then I will be using a positive value as my max, right. And this bias, right, this positivity bias that we have is called the maximization bias, right. So, the maximization bias is particularly bad when you use Q learning, because you are always using the max, right. When you use something like SARSA, it is less, but it all depends on your epsilon values, right. So, if your epsilon value is very high, then it is okay, but if your epsilon value is low, like we normally have in learning, right, if your epsilon is 0.1 or something like that, then with the probability of 0.9 something, right, you will suffer from the maximization bias even with SARSA, right. So, regardless of whether you use Q-learning or SARSA, there is this maximization bias that creeps in, right. But people typically think because Q-learning has the max in it, so only Q-learning suffers from the maximization bias, but that is not true. So, all approaches where you are currently using the max of your estimates, right, will suffer from the maximization bias, right. So, maximization bias does not mean that you are going to end up learning the wrong thing eventually, right. So, eventually you will approach the optimal action, right. So, this is basically telling you what fraction of the time that you are going left. The curve tells you what fraction of the time you are going left from state A, right. So, you have A and what fraction of the time are you going left from state A is what this curve tells you, and your epsilon is 0.1. Therefore, even after learning is done, you will be somewhere around 10%, right. So, at least 10% of the time, so you will be taking left, right, and remainder 90% of the time you want to take right, because epsilon is 0.1, okay. Actually, it is slightly better. So, 5% should be the optimal, because your 10% is split evenly between left and right. Okay. So, your 5% is your optimal number, right. So, that is basically what it is. But then if you use Q learning, you see that you start off with 50%, because the initialization your Q values will be all equal. So, you will choose to go left or right with equal probability, but then what happens is that you almost reach 100%. You do not quite reach 100%, but you almost reach 100% of going left, right. What is this percentage you will reach? You can't reach 100%, right. So, you will probably reach around 95%, right. Almost always you are going left, only the exploration, only when epsilon kicks in you are going right and you are going left, right. That is because in the first few episodes, right, you have not taken enough samples from state B, right. So, some action or the other from state B, right, is going to have a positive reward, right. Even if one action you take from state B had a positive reward, your value for left is going to get reinforced, and therefore you are going to keep going left, right. So, but eventually as you keep drawing more and more samples, the bias will go away, and eventually you will come back to learning something close to optimal, right. But what you really want is something like this, right. So, what you really want is something like this. So, you want to start learning from the beginning. You do not want to go up and down, but what you want to do is learn from that, right, without any bias, right. So, the problem from the reason why you are getting into this issue is the following, right. So, you are picking the max action, right, according to some estimate you have taken from some set of samples, right. You are taking what the max action should be, right, but you are also determining what the value of that max action is from the same set of samples. So, therefore, if one by chance that an action had a good set of samples to begin with, right, and then that will kind of reinforce. You are also figuring out which is the best action to do and what is the value of the action by using the same set of samples. Okay, this is a heuristic, right. So, people came up with this idea, hey, no, I should not be using the same set of samples. So, let us do the following, right. Let us use half the samples that you are gathering, right, half the samples, let us use that for figuring out which is the max action, right, and the other half of the samples we will use for figuring out what is the value for that max action. Clear now? So, that is half of the samples you take, you figure out what is the max action, right, the other half of the samples you take and figure out what is the value for the max action. So, how does this help? Because you are using two different sets of samples, the probability that you will overestimate the value for the action by both sets of samples, right, the probability that you will overestimate the value of the action by both sets of samples is small, right. Therefore, by doing this kind of split, right. So, even if you get the max value being overestimated by the action selection mechanism, right, the actual value that you substitute for the max action will come from a different set of samples, and that would probably not be overestimating the action, right. Therefore, you kind of mitigate the effects of the maximization bias. You do not solve it, but you mitigate the effects of maximization bias, right. So, how do I use these two different sets of samples? I basically learn two different Q functions, one with the first half of the sample, other one with the second half of the sample, right. So, how do we implement this in practice? We do the following, right. So, we have two Q functions, Q1 and Q2, right, and then for each episode I choose an action A, right. What is action A I choose? It's something that the action I am choosing to behave, right. I will use that using epsilon greedy on Q1 plus Q2, okay. So, that is fine. So, this is okay, this is the behavior action I am taking, I am not worried about it. Remember what this is Q learning, right. So, in Q learning I am not worried about what my actual behavior is because it is off policy. So, we can ignore that, and so I can choose an action A from state S using both the Q functions I am learning, right, Q1 and Q2. Now, what I do, I update the Q function 1, right. So, I update Q1 with probability half, I update Q2 with probability half. So, this part is fine. So, how do I do the update, right. So, remember I have to do the arg max according to one Q function, right, but find the value according to another Q function. Remember that is what we said, right. Using half the samples I will find out what is max, and using another half of the samples I will find out what is the value of the max, okay. So, basically that is what we do. So, we do arg max over A, right, find that using Q1, okay. But then once I find what is the maximizing action, right, I find the value of the maximizing action according to Q2, right. So, the target for Q1 comes from the Q2's estimate. Therefore, if Q1 is overestimating the value of that action, it will kind of reduce the value of the, sorry. So, if Q1 is overestimating the value of the action, it will reduce it by using the sample from Q2, right, using the estimate from Q2. So, that is basically how we do it. So, for updating Q1 we use the value from Q2, right, but the action that we pick to plug into Q2 is given by the current best action from Q1, right. Likewise, with the other half probability I update Q2. So, for the same sample, right, suppose I make one transition, right. So, what is the sample for Q learning? I have S, A, S prime, R. So, that is the sample for Q learning, right. So, for that one sample which I already have here, right, I initialize state S, I take A, I get the next reward and the next state, right. So, S A, R and S prime is the sample that I have drawn, and since I am using this coin toss, right, with half probability I will update Q1 or I will update Q2. So, the same sample is never used to update both Q1 and Q2, right, that is what I was telling you, right, half the samples you use for Q1, half the samples you use for Q2, right. Likewise, when I am updating Q2, right, I will find the max action according to Q2, but I will use the estimate of the value according to Q1 to do the update, right. You keep doing this until you terminate. So, that is the first loop, and then you keep doing this again and again for multiple episodes until you reach the end, okay. It is a very simple idea. It is a double Q learning has a very simple idea behind it, and again like I said, it is a heuristic. We can show that if you use double Q learning, right, both Q1 and Q2 will converge to Q star eventually, both Q1 Q2 will converge to Q star, right, and you can choose action epsilon greedily from the sum of Q1 plus Q2, or you can choose it just from Q1 or just from Q2, right, we do not care, right, it is all fine, but in either case it will all converge to Q star, right. And the nice thing is when I use double Q learning, it looks like the ideal curve that we wanted earlier. Remember we were talking about the ideal curve, right, and this looks like the ideal learning curve that we wanted earlier, and you can see that because it is not getting distracted by the maximization bias, it is getting to the optimal much more quicker than the original Q learning. Q learning also will eventually, if you keep extending this further, it will reach optimal behavior, but double Q learning gets there faster. This is not to say that double Q learning has eliminated maximization bias. It has reduced the maximization bias because it still there is a small, so it should actually go like this, right. So, still there is a small maximization bias, but this can manifest itself in other forms, right. If it is harder for you to actually sample the negative reward thing, right. So, if the there is some small positive outliers and then you sample that, sometimes those things can actually make it a little harder to get rid of the maximization bias. Okay. So, one thing to note about maximization bias, right? Maximization bias has been is existing in this RL formulation for a long time, right? It's just that until people started using powerful function approximators and started solving problems with large number of actions, right? Until they started using function approximator, the first thing with function approximators is that they are going to approximate the value, action value across multiple actions, right? So, even if you have sampled one action, the value for some other action can become very large and positive just because of the generalization, right. So, until we started using function approximations with the skew learning idea, the maximization bias was not really manifesting as a problem, right. It was there, right, but people kind of ignored it because eventually you learn, right. So, eventually you get to learn, right. Only when you started using function approximation, right, where I am saying I am going to use a neural network for representing Q function, right, not a lookup table, like we have been looking at putting things into a table so far, right, for the Q function. Instead of using a table, you are using a function approximator, right, like a neural network or some regressor and so on and so forth, right. So, when you start doing that, especially when you start using neural networks, you started seeing this kind of overestimation problem happening frequently. So, people thought, hey, maybe we should fix the overestimation problem, maybe there is something in the function approximation we should do to fix it. Then they realized that this maximization bias is what is really messing up the whole update. So, after that they came up with multiple techniques for adjusting for this maximization bias, and so double Q learning is one of these, and this kind of double learning, right, so double Q learning or double V learning and whatever, right. So, this double learning is something that you will keep seeing often when we start looking at function approximation and reinforcement learning in the later lectures.